what's the name of, is multi-pole the thing that passes it to lower vacuum spaces? Or?
No, these are inner multipole lenses. That's what we're doing right now. Right, so this is an inner multipole lens. Yep, you got it. Now, don't be surprised that these ones give you flat, because they really don't do much. Okay. So here's your second multipole.
The multipoles focus the beam?
Yep, they focus that beam and transmit the ions on down. They do the corkscrew. It doesn't apply in the back end.
Some things are just
what they
motive or the force to start moving.
The force they're ejected out of the trap with a good.
So basically, you just open the gate and they're normally bouncing around, and then they just typically.
Yeah. What we do is we don't actually just open the gate. What we do is we drop the bottom down and we push the top way up, and we blast them out. The front section. Yeah, you got it.
The size of that causes
Yep.
velocities of bouncing.
Correct. Yep, you got it. Now, I'm watching this to make sure. What I'm doing is between each curve, you'll notice there's a second when the spectra looks normal. And I want to make sure that it always comes back to normal and it hasn't just died completely. Okay? Because if it dies completely in between adjustments, you can save yourself. So right there, it comes back to normal and I see a spectrum. Okay? That actually looks like quite a nice spectrum too. I'm kind of happy with that. You excuse me for just a second. Notice we have a very different transmission calibration. Okay. Look at your height of your 195. Okay.
So this is bad or good?
Bring this up.
Well, it depends on what if you guys want high, you were very high biased. Okay. Now look at your 195. It's almost equal to your ultra mark. Okay. So you're very center biased right now. Okay. Does that make sense? Do you see what I'm talking about? Remember how the 195 was down here? You could barely see it. Now you've got about 50%. Now, it's still not totally unbiased because remember, the IT shows the 195 is the base peak. So now you're center biased. This is what I like the FT to look at like. And look at your injection time.
And how do you vary that manually, the bias of the instrument?
It's what masses you're using in your table. So you're coming off the automatic table, so you might have a different table over there. Okay, they don't have this, they're different tables.
Where can you check what tables?
I'll show you that after we're done. Okay. But this looks to me like what I like to see. And notice your IT time has dropped by 50%. So you're 2x better transmission than you were earlier.
Does that mean that the scan rate is twice as fast? If you can fill it?
Well, no, because this is you only change 10 milliseconds in your scan time of 800 milliseconds at 100,000 resolution. So the change is not appreciable. Not killer. Okay? And it looks pretty good. Okay? Now, right now we are looks pretty good, not too bad. Very little noise, looks nice. So now we're going to go to our next calibration. What's next? We did ion transmission, now we're going to do excite. Okay. For the 190 plus. And I'm still on the right mass range.
Excite of what? What is it?
This is excitation within the ICR cell. Remember the ions come in the center? And this is how far to the plates. Correct. I have a nice spectrum quality score, so I have a good chance of getting nice plots. And there's my optimal position. Okay. Here I'm getting I'm hitting the plates. And that's why my signal's dying. Okay.
This excitation is provided by what electronics?
This is the RF amplifier for the excite plates.
Oh, so there's two of those plates. Two are used to detect the passage of the ions, and two are used to excite.
Right.
Provide RF.
Right. So the excite plates are connected to your RF amplifier on your FT. And if you ever want, I can show you that in the back. It's that little box that's about 2 inches tall. Okay. And the other two plates are connected to that little piece that sits in the back of your trap.
Okay.
And if you ever shove your hand in the magnet, you'll feel there's that sharp board. That's your preamplifier. So that takes the signal, it amplifies it, and then it sends it over to the digitizer, and that's what digitizes the signal. Okay, now you'll see it does two excitations. It does the excitation 1 and then excitation 2. Don't ever look at the spectrum quality score for excitation 2. It's on a different scale. It's like a logarithmic scale or something. Okay. What it just did was it kicked you up to ultra high resolution. So it's actually right now it's looking at the peak shape versus excite to make sure it's not creating any weird anomalies. Okay.
Peak shape judged by what parameters?
What?
So peak shape judged by...
The way I understand it is if the two plates don't balance correctly, instead of the ions doing this, the ions I'm doing... They don't go out as a spiral.
The process of excitation. But once they're excited, then they're circular, right?
If we excited with both plates equally, if one plate excites more, they kind of spiral off in a weird direction, and we get weird peak shape problems. That's what we're checking here. Okay. And I don't exactly. Robert tried to explain to me, the physicist, and I just sat there. He explained it 4 times, and I was like, "Okay, Robert, whatever you say, I'll just take your advice." That. it's hard to deal with the Germans because they get really upset sometimes when we just can't, as Americans, understand something. And they'll just explain it over and over. And it's like, finally, I'm just like, I'm not going to be able to grasp this. Don't bother. Okay, now, it finished Excite. Excite calibration screws up your mass measurements. So the minute we're done with Excite, we always run mass calibration. So you don't have to run mass, it'll just happen automatically. Now, what it's doing is,